So here are 3 examples. These are not the kinds of questions that are going to get asked on the AP test, but I think we need to just practice what do RRAM, LRAM, and MRAM mean. So can we draw in the rectangles? So this first one asks, remember, if nobody tells you how many rectangles to use and where to have the rectangles to touch, you're probably not supposed to be approximating, and you probably shouldn't draw rectangles. But here it's been very clear, drawing the correct number of rectangles with the correct heights for each graph for the purpose of estimating the area under the curve from 0 to 6, from x equals 0 to x equals 6. So for this first picture, I'm supposed to use 6 rectangles and have their top left corners touch the curve. I've been given a hint that one of the rectangles have a height of 0. You see some black dots in the graph. Those are coincidental. Don't let them throw you off or make you think that they mean something special. I borrowed this picture from another purpose. So here, if I'm going to have x go from 0 to 6 and I need 6 rectangles to cover that, that's okay. That's easy. That's going to be 1 unit wide for each rectangle. So I'm going to have 6 rectangles. That means the first rectangle is going to go from x equals 0 to x equals 1. I'm supposed to have the top left corners touched. I've been told that's LRAM. So I would think about the left-hand side of the interval from 0 to 1. That's where x equals 0. I'm going to use that as my input. So I'm going to go to the curve and I'm going to try to find where x equals 0, what's the y value? Oh, it looks like 0. So that turns out to be my mystery rectangle, the one with a height of 0. So when I add in the area to this sum, that's going to have an area of 0 because a width of 1 and a height of 1 multiply to give an area of 0. My second rectangle is going to cover the interval from 1 to 2. So I think about the left-hand side of that interval is 1. I'm going to go to the y value that occurs where the input is 1. And there's a dot there. That's just a coincidence, but it's convenient. So I'm going to draw in this rectangle, which happens to be a square. My next rectangle is going to cover the distance from 2 to 3, the left-hand interval. The left-hand side of that interval is 2. I'm going to go to the place where x equals 2. I'm going to draw this rectangle. When x equals 3, I'm going to find the height of my curve. Kind of seems like it's right there, so I'm going to draw straight across to give me this rectangle. All these rectangles are going to have a width of 1. My next rectangle, it just happens to be, this is the first rectangle I'm going to draw that isn't, sort of overestimates the curve, the area under the curve. But when I come to the place where x equals 4, I find the y value, and I use that as the height of my rectangle. And here's where x equals 5. Notice for an LRAM approximation from 0 to 6, I never considered the height of the curve at x equals 6. I considered the height at x equals 0, 1, 2, 3, the height at x equals 0, 1, 2, 3, 4, and 5. And that's 6 rectangles worth. In this middle picture, I'm going to use 3 rectangles and have their top corners touch the curve at the top right corner. So have an interval from 0 to 6. When I chop that up into 3 pieces, every piece is going to be 2 units wide. So my first rectangle is going to cover from 0 to 2. So I'm going to go to the place where x equals 2, the right-hand side of the interval. I'm going to find that height. It's here. I'm going to use that as the height of my rectangle. My second rectangle is going to cover from 2 to 4. The right-hand corner of that, the right-hand edge of that interval is 4, so I'm going to go to the place on the graph where x equals 4 and use that as my height. Remember, on the AP test, nobody cares how good this approximation is. You've been told how many rectangles to use and how to have them touch the curve. That's what you're going to do. And then my third rectangle is going to cover the interval from 4 to 6. The right-hand edge of that is 6. So I go to the curve where x equals 6 and I find the height. Happens to be 0. So, okay, that means I'm going to have one rectangle whose height is 0. So these are my 3 rectangles for RRAM in the middle picture. The last picture, I'm going to have two rectangles, and I've been asked to have their midpoints touch the curve. So have the rectangle touch the curve at the midpoint of the interval. Well, to go from 0 to 6 over two rectangles, that's going to be a 0 to 3 rectangle. 1, 2, 3, and a 3 to 6 rectangle. So my 0 to 3 rectangle, what's its midpoint? It's going to be 1.5. So I'm going to go to the place on the curve where the input is 1.5. That's halfway across this interval, and I'm going to come up here to find the height of that rectangle. I'm going to use that as the height of a rectangle. A rectangle needs to have a width of 3 and a height that is equal to the function value, the y value on this curve at the place where the input is 1.5. My second rectangle is also going to have a width of 3. It's going to cover from 3 to 6, halfway between 3 and 6. The midpoint between 3 and 6 is 4.5. And the place on the graph where input is 4.5. Does that kind of look right? I'm going to use that as the height of my second rectangle, except it's going to be a better rectangle. It's supposed to be a rectangle. There we go. So those will be the two rectangles I use here for MRAM. So we have a name for the result when we use rectangles to approximate area under a curve. After Mr. Riemann, we call this a Riemann sum. So sometimes on the AP test, instead of seeing use an LRAM approximation, you'll see instructions that say use a left Riemann sum. That's the same as LRAM. Or use a midpoint Riemann sum, means the same thing as MRAM. And this approximation is only very, very rarely going to be exact. I reserve the right to ask you when it would be exact. Think about that. But the big idea, the big thing we want to notice is that if you use more rectangles, your answer is going to be closer to the true value of the area under the curve. There are two kinds of error that we can be sure of when we use a Riemann sum. If we find the area under a curve, that is increasing. So if we find the area under a function that is increasing, the Riemann sum approximation, a left Riemann sum will always give an underestimate, and a right Riemann sum will always give an overestimate. I'll leave that to you to think about why that's true. If a function is decreasing on an interval a to b, and I try to approximate the area under that curve between a and b, then a left Riemann sum, a left rectangle approximation method process, will give an overestimate of the actual area, and RRAM will give an underestimate. So we have this example is from an actual AP test. Rocket A has a positive velocity after being launched upward. The rocket's velocity is shown here in this table at certain times. We don't know what the missing times are on those intervals that aren't for the t values that aren't shown, but we have been told that v is increasing, at least over the whole interval that we have information about. So question A, use MRAM with 3 subintervals of equal length to estimate the distance traveled by the rocket on the interval from 10 to 70 seconds. So some big things to notice here. We've been told exactly how we should decide where our rectangles touch the curve. We've been told MRAM. We've been told 3 subintervals. That's the same as saying 3 rectangles. So one slightly tricky thing about this problem is they've asked us to give an answer about distance traveled, so area under velocity curve. But they didn't use the whole interval that was given. They said just between 10 and 70. So we're going to need the area under the velocity curve between time 10 and 70. And since we don't know anything about the velocity curve, even once you know all the tricks from the rest of chapter 5, you won't have enough information to find the exact area. So we're going to use an approximation. I'm going to use 3 subintervals. That means I need to take the distance between 10 and 70 and split it up into 3 equal chunks. They will never give you chunks that don't work with the table of values they gave you. So the difference between 10 and 70 is 60. 60 divided by 3 is 20. So every rectangle is going to cover an interval of 20 seconds. So I like to draw these in. That tells me I'm going to go from 10 to 30, from 30 to 50, and from 50 to 70. And I actually draw that in my chart just to kind of keep me focused on 3 rectangles. Now, this is the first time we've been asked to give any kind of Riemann sum answer, and we haven't been given a picture. So at this point, you might decide that you would like to plot these points on a graph and sort of draw the rectangles in. Your goal by the end of sort of this notes section and the practice problems we do is to be able to answer without making the picture of the rectangles. But, to be honest, nobody's ever going to mark you down. Nobody's going to give you negative points for drawing rectangles, so do what you got to do. But how do we find the area of a rectangle? You're going to find the base, the distance across the base, which I just said for all 3 of these rectangles is going to be 20 seconds, right? And I'm going to multiply by the height of the rectangle. Well, how tall should I make my first rectangle? Well, my first rectangle covers times from 10 to 30, and I'm supposed to use the midpoint. Well, the midpoint between 10 and 30 is 20, so I'm going to use the input value 20 to tell me what output I should use as the height of my rectangle. So 20 seconds times 22 feet per second. That was the first rectangle, and I have 3 rectangle areas to add up. So plus 20 seconds times, what about my second rectangle? It covers from 30 to 50. Halfway between 30 and 50 is 40. Tells me I should use a height of 35. Units are feet per second. And my third rectangle covers from 50 to 70. The midpoint is 44. The height, the midpoint is 60, and the height at the midpoint is 44. So this is going to be 20 seconds times 44 feet per second. And notice for each of my 3 rectangles, I have rectangles. I have units of seconds times feet per second, which is going to give feet. So I'm going to add feet plus feet plus feet. And I'm going to have a result of that's 440 feet plus 700 feet plus 880 feet to make 2,020 feet. It would be atypical on the AP exam for them to ask you 2 Riemann sum questions in a row. So I modified this question just so we could get some practice. I think this table of values and this idea of approximating area under a velocity curve to find total distance traveled is a good way to practice right now. So here, use RRAM in 2 subintervals of equal length to find the distance traveled by the rocket over the interval 0 to 20. So, whoops. I know I'm going to go from 0 to 20. And I need 2 rectangles. That's not so bad. 0 to 10 and 10 to 20. And I'm going to have my top right corners match. So top right corners, I'm going to multiply distance across the rectangle, so width of the rectangle, which is measured in time units. Each of these 2 rectangles has a width of 10. So this is going to be 10 seconds times the right-hand edge of the interval 0 to 10 is 10. So I'm going to use the output value at that right-hand edge, which is 14. That was 10 seconds times 14 feet per second. Plus, my second rectangle also has a width of 10. I won't guarantee you that on the AP test all the widths will be the same, but here they happen to be. And my top right-hand corner, that's going to be the output when the input is the furthest right in the interval 10 to 20. So that gives me the 22. That's 10 seconds times 22 feet per second, which gives me, remember seconds times feet per second gives feet, so this is 140 plus 220 feet, which is 360 feet. I'm going to leave all my work there and just answer the second part up here. the second part, is that your answer, this 360 feet answer, an overestimate or an underestimate of the true distance traveled by the rocket on that interval? So I know that my velocity function was increasing. So imagine an increasing function, and I used RRAM. That means I had my rectangles line up with their right corner. So my question, can I tell whether my answer is an overestimate or an underestimate? So this is summarized in that box at the top of the same page. So if you like to memorize the box, that's fine. If you like to draw yourself a picture every time, Mrs. Hicks does, then whichever one is fine. We have to either remember or draw yourself a picture and notice that every rectangle you drew was too big, right? So if we use RRAM on an increasing function, then our answer is too big. It's an overestimate. So I'm going to write up the answer. Notice the justification I give. So I wrote my answer, 360 feet, is an overestimate of the distance traveled by the rocket because v of t is increasing on the interval 0 to 20. That is sufficient answer because v of t is increasing. So don't make the mistake of thinking that you need to say because every rectangle I drew is too big. That's not what they're looking for. We're looking for a write-up based on this version up here. For any increasing function, if you use an RRAM approximation, your result is going to be an overestimate. If you use LRAM on that same function, increasing function, your estimate is going to be an underestimate.